when I was young, Israel worked on improvisation, and I think you definitely, we were brought back in the former session back to the days of improvisation, and improvisation has some good features and has some bad features. So one of the bad features is that actually I was planning to start with thanks. So I would like to thank, first of all, the Academy for agreeing to have this event. I would like to thank, I don't know if he listens to us on Zoom or not, Professor Istvan Hargitai from Budapest, because he was actually the person which alerted the Academy, Professor Chachanover and Professor Moti Segev, to the fact that there will be the 100th year, and they approached the Academy asking them if they want to address this event. So I want to thank Istvan for that. Then I would like to thank Marek Karliner, who helped enormously, without whom this would not be possible. I would like to thank Moti Segev for agreeing to have the committee work the way it worked, so I appreciated that very much. I would like to thank Dr. Yael Ben-Chaim, who worked tirelessly in difficult circumstances for her for quite a period in order to make this event possible. So I want to thank all of them. Please. Now it's my pleasure to call one of the whatever hierarchy, grandson, nephew, or whatever way.
Grandson.
Grandson who sits on the cathedral, the chair of Yuval Ne'eman at Tel Aviv University. Yuval was always very interested in space and cosmology, and there is a lot of turbulence there. So we would like to hear about that, not to mention some local turbulence.
Okay, thank you. Okay, thanks for the invitation. Yeah, I have also lots of stories about Yuval. I'll tell you only a few of them. Actually, the first one is that I met Yuval first around 98, 99. I was at the time at CERN, and he came to visit with the Minister of Science Matan Vilnai. And the reason I remember that day very clearly is because there was a dinner at the embassy, the Israeli embassy in Geneva. I was invited, but I was ordered to come with a tie. Now, no physicists have a tie, so that was the day I got my first tie and I learned how to put it. Later, when I came back to Israel, Yuval would invite me to his office. He wanted to, to know a little bit about what's going on. At that time, ADS-CFT was really still, in the main topic. And in return, Yuval would tell me lots of stories. Some of them you heard from Eliezer. One of them, for instance, if you haven't heard yet, was that the Israeli poet and also partisan Abba Kovner came to Yuval and asked him to explain how laser works. And Yuval told him, look, imagine the Chinese government tells billion Chinese to stand on the table and jump at the same time. This is a laser. And then there is a poem that he gave me, maybe you've seen it, by Abba Kovner, about million Jewish kids pounding the ghetto and nobody hears them. Anyway, Yuval, there are lots of stories about him, but he was actually interested a lot in gravity. In fact, when he was the attaché, the military attaché in London, he went to do his PhD, he wanted to work with Hermann Bondi, but Hermann Bondi was at Cambridge, and Cambridge was far. So he looked at a place close to the embassy, and he found Imperial College. And then he went to Abdus Salam to get accepted as a PhD student. Abdus Salam, as was said before, was Pakistani. And Yuval had a recommendation letter from the Minister of Defense, Dayan. Anyway, he was accepted. The rest is history. So there are lots of stories about Yuval. And actually, the topic I want to talk about is an interesting problem, but the way I got to it is because of gravity. And I will tell you what is the challenge, Actually, there are several challenges, mathematical, physical. I will mostly concentrate on the physical, even though David discussed the one which gets you, the one of the millennium problems. Then I will tell you a little bit of precision turbulence. Actually, what is required in this field is something that happened in cosmology. Cosmology were lots of models. But then when Planck gave the data, before that also WMAP, that's it. I mean, many of these models just became irrelevant. I will tell you about a solution that I propose, and you will see something amazing about precision turbulence results that we have so far now. I mean, they are not published yet. And then I will tell you something curious that I started to look at. I ignored, by the way, the part on holography, not because it's not important, because of time. Then I will tell you a little bit about deep learning. Each one of them is each one of us is playing with LLMs, with ChatGPT, etc., etc. What can machine learning tell you about turbulence? And then some outlook. The problem is quite old. Da Vinci has these plots of turbulence of the Arno River, like 500 years ago, and the problem was, I mean, pretty much known. Something is happening, and it's very easy. I mean, you go everywhere and you see turbulence all the time, which makes it embarrassing for us as a physicist. We didn't solve this problem, but has lots of data around. But why the problem is difficult? It's actually considered major unsolved problem. Definitely in classical physics, the major unsolved problem in classical physics. And it has these things that the principles or the rules are very simple. Really, Newton's equations, nothing simpler than that. But then the emergent structure is very complicated. It has all the signatures of a complicated problem. Large number of degrees of freedom. Strongly interacting. There is no small expansion parameter, and it's also very far from equilibrium. So all the things that make life difficult. And the reason I got to think about this problem is because of gravity. Actually, general relativity is not a dissipative theory. But if you have a black hole has a horizon creates dissipation. Basically, classically, what goes in doesn't go out. And in fact, people thought about it before. It used to be called the membrane paradigm. People tried to assign some fluid structure to the black holes, but it didn't work for them. And the reason why it didn't work is because they were thinking about black holes in asymptotically flat spaces. They have spherical topology, and the small expansion parameter that you generate is of order 1, so you don't really get Navier-Stokes. So notably, Damour and many others worked on it. But then it came as a spin of ADS-CFT. Sometimes people call it fluid gravity correspondence. And in ADS-CFT, the situation is different because the black hole can be planar and you can separate scales, namely the scale of the perturbation or the mean, let's say the mean free path from the scale of the size of the typical size of the system. And therefore, you could actually get Navier-Stokes equation. It's very, very simple. If you take the horizon and you look at the evolution of the horizon under perturbation, if you go to the non-relativistic limit, you just get exactly Navier-Stokes equations. And the way the map works is that the deviation from equilibrium is the pressure, and the normal is the vector field that describes the fluid. There are two other coordinates which are neglected, but they are not important. When I noticed that fact many years ago, I was really impressed because I said, okay, what does it mean? It means that every solution to Navier-Stokes equation you can map to some geometry. So therefore, summing over all Navier-Stokes solutions is like summing over geometries. But what is this? This is called random geometry. And that's the story I want to tell you. Okay, but let me begin 200 years ago with the Navier-Stokes equations. And as I said, they are very simple equations. There is a velocity vector field, V, and it has indices I, and I can go from 2 to whatever D that you want. 1 is a different model. This part is just the acceleration. And this part are the forces. So it's Newton's second law. The reason why you don't see the mass is because it's incompressible, so the density, basically it's 1. And so these equations, you see they look simple, but they are quite remarkable because this is the nonlinear part, but there is no small expansion parameter. It's like an order 1 coupling, what we call in quantum field theory. The only expansion parameter is the number of dimensions, But if you go and d goes to infinity, it doesn't simplify. So the competition is between nonlinear term and the viscous term. And if the viscous term wins, then it's a very smooth thing. If this nonlinear term dominates, then it's a very complicated structure. And as you will see environmentally in nature, because of the numbers, namely the viscosity, the values of the viscosity, we always see turbulence all the time around us. It's just related to this property of that. These are external forces that you could add, and in principle, I mean, this velocity, this pressure is related non-locally to the velocity. So the only thing you really need to give is the solutions of this velocity field. This is one of the millennium, one of the 6 millennium problems in mathematics is just something very simple. Show that if you start with reasonable initial conditions, let's say in reasonable boundary conditions, there are no finite time blowups. Namely, the gradients of the velocity field don't blow up. Looks like a simple problem. It's a huge problem in mathematics. It's not unrelated to something that we know in gravity, which is called the cosmic censorship. Will you have curvature blowups without the horizon? Because the gradients of the velocity are like curvature. But that's a different story, and I'm not going to talk about it today, but there are some interesting things to say about that as well. There is an important dimensionless parameter in the problem that actually compares the nonlinear term and the viscous term. And it has in it the scale, characteristic scale of the problem, the velocity, or basically velocity differences at that scale divided by this number, which is the kinematic viscosity. And what people noticed is that phenomenologically observation is that when this is of order 10 to the power 3, you see something called turbulence, which I will define, which people try to explain. Before that, it's like a laminar flow, then chaotic flow, etc., etc. Order 10 to the 3, this is the phenomenology. There is no explanation for this number, but this is kind of universal. It doesn't mean whether it's air, water, electron fluid, it doesn't matter. System doesn't matter. So here is a river, and the reason why I say that this Reynolds number are so huge, here is 10 to the power 7, is because if you look at this viscosity, for water is 10 to the minus 6, for air is almost 10 to the minus 6. The reason for the difference because you have to divide by the density. So you see, if you have such a number in the denominator, it doesn't matter what you do. You just spin with your spoon in the teacup, you will get the turbulence. You swim, you'll get turbulence. Okay, so now what does it mean to solve turbulence? I mean, if you change a little bit the initial condition, you get something totally different. So what does it mean to solve turbulence? I mean, there's no way to track all these things. So people I had the idea of studying statistical turbulence. They said, okay, suppose we average over data, over solutions. Will we get something which is universal? And then it turned out that the story is correct. If you define scales which are smaller than the size of your forcing, bigger than the molecular scale of dissipation, you are far from all this non-universal structure, and then there is the universal property of turbulence. Now, of course, nobody proved it. It's not proven mathematically. There's experimental, numerical evidence. Nobody proved that this is correct. But it turns out that turbulence reaches a steady state that exhibits statistical homogeneity and isotropy. Now that reminds you of quantum field theory that has translation invariance, rotation invariance, and it's Euclidean because forget about the time for the moment because it's steady state, which is kind of an interesting thing which we will use. But you might be wondering how is it possible that it reaches a steady state? That means that the distribution function of this whatever it describes as statistical turbulence is time independent. But that means it's a conserved quantity. But there is no conserved quantity in the problem except energy that goes from scale to scale. But if it's equilibrium and the energy is conserved, that's the Gibbs distribution, but it's not equilibrium, so what is it? It turns out that this probability distribution function is in fact a non-local object. And that's why it's very complicated. Okay, so what are the observables that you would like to calculate? So for instance, one of the main observables is let's think about it as a wave, and then take the velocity vector fields at 2 points. And what you do with it is you dot it with the vector that connects them. This is called longitudinal. You can also dot it with the transverse. It doesn't matter. This will be called transverse observables. And then the only thing you're going to do is average over solutions. Or if you want average over the force, it's the same thing. The remarkable thing that people discovered is that all these objects scale. They don't. They because of high isotropy, they depend only on this size R, but they scale with some numbers. And this is an infinite set of numbers. In principle, they are real numbers that are universal to any physical system that exhibits turbulence, except it depends on the dimension. Will be different numbers in dimension 2, 3, 4, etc. But other than that, it doesn't matter where you look for them. And the task will be to explain these numbers. Now, if you think about, usual stuff in conformal field theories, people ask you, give me the anomalous, or quantum field theory give me the anomalous dimensions. In some sense, it's analogous, but this is a system which is out of equilibrium. There is no measure with which we know how to calculate. That's what makes this complicated. Okay, so I hope the problem is clear. Task is to get these ones. And actually, embarrassingly enough, the most important result in this field is not by a physicist, but by a mathematician. It's called Kolmogorov. And he actually used what we call today mean field theory or dimensional analysis. He basically assumed the scale invariant structure of the probability distribution function. And he told you that all the numbers will be very simple rationals, n/3. That was in 1941. Very soon afterward, it was clear that the answer is incorrect, even though many people still think that Kolmogorov scaling is correct. I will explain why it's incorrect. But anyway, what Kolmogorov told you is that all these structure functions that I told you that are complicated, they have this very simple linear relation. And typically you see that for the 2-point function, when you do the Fourier transform, it looks like this Kolmogorov scaling. He knew, everybody knew at the time it's wrong, and there is actually a very nice story written in the books about a meeting at Kazan where Landau was telling him that this can be correct, etc. Anyway, but it looked pretty close to the data at the time. But what's wrong? What's wrong? Why this is wrong? There is a reason, there is a deep reason why it's wrong. This is called intermittency. So what Kolmogorov assumed is that there is a self-similar structure. And the self-similar structure, I zoom in and I will see exactly the same structure as at large scales. This is called the fractal structure. He assumed that, and that turned out to be wrong. If you look at the velocity profile, you will zoom at different times or at scales, you will see totally different things. And this is not a function of turbulence. It's just I gave an example of what's called Cantor's function, which is also called the devil's staircase. If you zoom here, you'll get something. If you zoom here, you'll get something else, etc. So what is missing in Kolmogorov's story is known. It's intermittency. Scale invariance is incorrect. In the language of anomalous dimension, it's not one. There are actually infinite number of anomalous dimensions there. It's not one. And here is the structure. So if I look at the anomalous exponents as a function of this n1, 2, 3, etc., these are the anomalous exponents, Kolmogorov will tell you that it's linear. If you go to moment 3, you can prove analytically it's 1. This is the only one that you can prove analytically. And the rest, there is some function on which you know some things about its convexity properties, but nothing more. This is related to two one dimensions. I will not discuss it at the moment. Now, you are supposed to give this. In fact, it's not only at integer numbers. You can just give the curve. So those of you who remember the story about quantum gravity, if somebody tells you, I have a theory of quantum gravity, one of the things you would ask, okay, show me the page curve. Derive for me the page curve. It's actually, in a sense, analogous. Derive for me this curve. Tell me what it is. That's the challenge. The separation from n/3 is the intermittency. Okay? Now, let me offer you a solution. I will explain the logic and I'll show you evidence. Okay, the solution is actually very simple. If you want to find these anomalous exponents, this curve, solve this equation, where this is a number, fixed number, which depends on only on the number of dimensions. It's a quadratic equation. Okay, so this difference is what we call intermittency. So this is the intermittency parameter. Set it to 0, you'll just get Kolmogorov scaling. Set it to some other number. By the way, that number should be derived. It's not, you cannot, it's in any dimension, it's one number. And the interesting thing about this formula is that if you go to very large n, what you see is that this anomalous dimension scale like square root of n. That's something unheard of in the turbulence community. I'll show you that it's either linear, goes to a constant, not square root of n. Those of you who worked on string theory know that square root of n appears all the time, like the mass related to the level of the string, etc., etc. Okay, so that's the proposal. Now, when we looked at that proposal, and I will explain the reasoning for it, the only data that we found, and actually it's mostly what we have until now, is up to moment 8 or 10. It's not very good resolution. Of course, you could fit it, but you could fit it with many, many other functions. It's not a big deal. So that's not a very strong evidence. And now I was trying to convince my friends to do the numerical calculation at least, not the experimental. And they always told me that it's impossible. Okay, it's difficult. So we decided to do it. Before that, we started on smaller problems. So collaborators are Slava Mukhanov, well-known cosmologist that you know, and James, who is also working in cosmology. So it's good to have these guys because they know something about numerics. And we started to go for smaller problems. For instance, these are well-known called shell models. They are basically truncations, huge truncations of Navier-Stokes equations to nearest neighbors fluid elements. They are well-known textbook models. And we try to calculate the moments, to very large. You cannot see, but there is some anomalous scaling here in this model. It's just very difficult to see it. Okay, we did that. We did the real model. We got convinced maybe we can go for the gold. Okay, so I started to do the other one. Now, this first result that we got up to moment 40. And this is the model, this is this formula, the quadratic formula that I'm telling you about. It does pretty well. This is the well-known model in the literature of the turbulence people. I mean, that's a textbook model. It grows linearly at some point and it starts to deviate. It doesn't look like it's going to go linear. Then we went to 60, okay? And now you see that the model, this quadratic model, quadratic equation does really, really very well. All the others, this goes to a constant, this goes to linear. These are the competing models, let's say, in the literature. They don't seem to work correctly. We now work on this is huge errors, but we can reduce them. But it looks like the pattern is correct in the sense that the formula does capture correctly the physics. Now, those of you who thought about probability before would tell me that it's impossible. To get to a moment 60 or whatever, 80, you need an exponential number of data. How is it possible? Turns out something amazing happening to this probability distribution function of turbulence. They are not the things that we are used to. They drop very, very fast. They flatten very, very fast. They cannot get to very large velocity fields. Maybe the reasoning is because it's a non-relativistic theory. I don't know the reasoning. But that's the only reason why we can do that. By the way, the amount of data we collected for that is about 20 terabytes. It's like 20 times the data that Planck's mission had. So it's really a huge amount of data. Yeah.
P here is what you call n before?
Yes, sorry. That's to confuse the reader. Yes, I'm sorry. Yes, you're right. Sometimes we call it P, but yes. So it looks pretty amazing. I hope it's correct. I don't know. It's still not published because if you want to send something like that, you really want to be sure and also give the data to everybody to check because it's, yeah. Anyway, that's the story. So that's the story. And let me tell you a little bit about why is it interesting. Okay, you say, okay, so you found the phenomenological formula. I mean, who cares? Okay. No, there is a story behind it which I think might be correct for systems out of equilibrium. But first of all, let me tell you what is the origin of that formula. By the way, that formula is called in 2 dimensions. This formula I wrote was not in 2 dimensions. It's called the KPZ formula, Knizhnik-Polякov-Zamolodchikov. That paper appeared when I was a student. I was really impressed. That was a solution of 2-dimensional quantum gravity. I think, David, you were working on that, many of the people. The idea is the following. Suppose I tell you that I have a certain dimensions of curves, dimensions of operators, whatever you want, but they were measured with respect to a flat measure, Euclidean measure, Lebesgue measure. And then somebody tells you, okay, but do the following trick. I want you to do it not with respect to the Euclidean measure. I want to put in front here e to the gamma phi of x. Gamma is a number, but this is a Gaussian free field. In 2D, it's called the dilaton. Okay? It's a mathematical problem. It's got nothing to do with two-dimensional quantum gravity, anything. Just solve this problem. The answer is the KPZ equation. Now, you could ask, why should we have random geometry or all these things in turbulence? I mean, it's just flat space, okay? So here, actually, that's something cute that I realized, took me a while, but when I realized that, it was a breakthrough, at least for me, it was a breakthrough. In order to have this random geometry, you need this dilaton. Where will you get the dilaton? Dilaton, well, maybe you can get it from symmetry breaking. But which symmetry breaking? It turns out that if you want to think about Kolmogorov scaling, you can think about it as a spontaneous symmetry breaking. Why? Because if you look at the Navier-Stokes equations at the inertial range, it's well known that they have two symmetries. You can scale space and time independently. Sigma and z are two independent parameters. But then there is a flux in the system that goes from scale to scale. That flux carries dimension under this, and it breaks it to a diagonal part where z is 2/3. This is Kolmogorov scaling. Now that's very interesting. It's not a dimensional argument or scaling argument. It's actually an argument about spontaneous symmetry breaking. Now, for us that's amazing, because if this is true, then what the next step I would do? I would look for the dilaton or the Goldstone boson. Okay, but you have to cook up this action for that dilaton. And that turns out to be that by symmetries, it's a generalization of what we call Coulomb gas in 2 dimensions. You can add terms to that and it will look like a generalization of the Liouville theory. And basically 2D, this will be like the curvature term, and this will be the Laplacian. In higher dimensions, these are known as conformally covariant operators, and this is so-called the Q curvature. Is an object which is not topological invariant, but the integrals are conformally invariant. Details are not important. There is you can build such a theory. And then you can follow the things that people did in 2 dimensions. It's a similar philosophy, of course, in D dimensions, and you will derive the formula. So now you could ask me, okay, great, you derived the formula. It's not true. There are 2 main assumptions here hidden. One assumption was that there is a steady state and I can forget about time. Okay, maybe that's reasonable, but nobody proved it. And the second assumption is that I didn't know exactly how the dilaton couples to this mean field theory, which I call the K41. I didn't derive it. I assume that it's like, the way it couples in other theories, but maybe it's wrong. Okay, by the way, there is another way I can derive also a formula for this thing from conformal anomaly, but it's not very important. Anyway, summary of the story. This should solve the equations. This should solve Navier-Stokes in any dimension. Hopefully it's correct. We'll see in the future. Okay, let me now entertain you in 3 minutes with something else. At that point, when I thought that there is no way to calculate anything, numerically, etc., I thought maybe let's go to deep learning and see what it can do. And I'll show you only 2 things. There are many things can be done here. First thing, the question was, can the machine learn to solve Navier-Stokes equations? What does it mean? I pick many solutions. I give initial condition and a solution at time t. Another initial condition, solution at time t. And then I give a new initial condition. It didn't see it before, and I asked to tell me what's the result at time t and also what's happening in between. Turns out it can do it. It solved it. And it doesn't care whether it's a Navier-Stokes equation, it's something else, etc. I'll show you a little bit of, this is called Burger's turbulence. It captured correctly the shocks, etc. But there are 2 main questions which are unanswered here. First, is it really true? Or once it gets into the turbulent regime, that's it. At some point it will get lost. because it's a different initial condition, but there will be this exponentially a pool of exponents. And the second question, which is not answered, is this RG property. If I solve it at the scale A, lattice size A, will it be able to tell me correctly the lattice size A over 2? Namely, it really captured the physics of the problem. And these are two problems that were not answered. The second was another interesting thing. You know that we have all these generative models that you can generate faces of celebrities, etc., etc. Can the machine generate solutions to Navier-Stokes equations in the following way? I will give it plots, actually pictures of fluids that were actual solutions of Navier-Stokes equation. I'll give it 1,000 of them. And then I will ask it to generate new ones. Will the new ones, now if you look in the eye, you will not be able to tell me that this is what the machine generated. By the way, there are different solutions, you can check. But how did we check it? We just calculated from it the Kolmogorov scaling. That was in 2 dimensions, so it's Kolmogorov scaling works. And it turned out it's correct. Okay, so now it's great. The reason why I went to do that, because I thought it will give me millions of solutions and therefore a great statistics, and then we don't need to solve Navier-Stokes equations. It turns out life is more complicated. It's true that the solutions are different, but it looks at the moment that what the machine is doing is not covering really the whole space of solutions. It stays locally in the regime that you gave her. Namely, it's not going to identify the rare events, the hurricanes, the ones that dominate the high moments. So I don't know the answer whether it is able to do it or not, but that's an open problem, but it's interesting. Machine can learn turbulence. Okay, that's this. You can see that it captured correctly the scaling, etc. So it did pretty well. By the way, we also identified how it did it, because we identified that what the property that it was using is really Kolmogorov scaling, because we were cheating it with a certain Kolmogorov scaling and some other noise at high moments, and it thought that it's turbulence. So anyway, yes, okay. Yeah, I'm on time. I'm checking the laser. Don't worry. It will be great if one can have some experimental data, which is really good. And it looks like all these experiments, I don't know, with wind and water, they are probably hopeless. Maybe something else is needed. There are lots of interesting structure about not just anomalous dimensions, but also multiple correlation functions. I didn't tell you about holography. This is actually very exciting, I think. All the turbulence information is encoded in the fractal structure of the horizon. But exactly how, that's not clear. And then this will be fun, I think, if deep learning can help with turbulence. Yeah, I think I'm almost okay, thank you.
Yaron was on time, so one question, please. The microphone to you, please.
Sorry. Way of calculating how much information you provided to the learning algorithm by giving it this photo, to be able to get a theoretical sense of like what's the maximal output that you could get. Physically speaking, not creating.
I understand the question. I understand. They are good. It's a good question, but there are many definitions of what is the amount of information that you need. Okay, it could be, for instance, the number of samples. It could be the information in the samples. So let me answer it in another way. Okay, another thing that we checked is whether the machine can identify turbulence from chaos. Okay, and compare the complexity of this to identifying cats and dogs. What would be your guess? What is the more difficult, cats and dogs or turbulence and chaos? Easier turbulence and chaos. The structure there is actually, there is a lot of structure there, and the machine identified it easy. So, and there's a measure of what I mean by more complicated. So the complexity of cats and dogs for the machine was larger than turbulence and chaos. Yeah.
Okay, I will ask you, where is the violation of the Mermin-Wagner theory that allows in 2 dimensions.
Systems are not in equilibrium.
Okay, so this is
The whole framework is very different.
okay. Thank you very much again.